Hello. I'm going to start right now. I'm setting up the homework actually at the same time. Okay. No one's here, but it doesn't matter. I can still edit this video later. Okay. So before, you guys were dealing with logarithms, and you guys were just setting them up and rewriting them. A couple of rules that you guys went through already were, if I write, so log, rules. So we had the power rule, and that went log of a to the b value. We said was bring down the exponent to b log of a, right? We had our dividing, which was our change of base, log a of b over log a of c. As long as the bases are exactly the same, we change the base to log base c of b. And then I think another one that you guys did was going the other way. Change of base also goes the other way. Log base c of b is, darn it, that's ugly, is equal to log of anything b over log the same anything of c. Example of that is if I say log base 3 of 5, you can write this as any base you want. Log, you can call it log common log. You can say this is log base 4 of 5 over log base 4 of 5. This could be log, this could be ln of 5 over ln of 3, natural log of 5 over natural log of 3. Both of these are perfectly fine. Okay, so today I want to go over some other rules. Just again, we covered this again in class. You guys will be doing this a little bit in the work. We have addition. Addition was log base a of b plus log base a of c equal to log base a of parentheses b times c. Because if you're multiplying, if you're adding means multiplying. This is also on the adding on the outside means multiplying on the inside. As we talked about this before, we have a subtraction rule. It's log base a of b minus log base a of c. It's log. If adding is multiplying, then subtraction has to be dividing. So subtracting really means division here. On the outside, subtracting on the outside means division on inside. So, like a dumb illustration of this, if I say log base 2 of 8 minus log base 2 of 4, if we do the math, this should give us log base 2 of 8 over 4, which is really log base 2 of 2, which turns out to be 1 of our identities. Well, if I remember correctly, my slogan is logs solve for exponents. And when I say log solve for exponents, looking here, 2 to what exponent is 8? Because log solve for exponent. What exponent is this? 2 to what exponent is 8? That's going to be 3. And 2 to what exponent is 4? 2 to the second power. That gives us the one we wanted. So on IXL today, a good practice would be evaluating logarithms properties. So let's go take a look at these. They want us to rewrite this in simplest form. Now, our rule for logs, so logs are inverses of exponents. So if I say log base 2 of 2 to the third power, the answer is 3. Now, why is that? Why is this 3? Well, there's actually a couple ways we can do this. We can say, hey, well, isn't this the log base 2 of 2 cubed is 2 times 2 times 2 is 8? Well, 2 to what exponent is 8? That's 3. That's one way of doing it. We can use our power rule, where we say log base 2 of 2 cubed. The 3 goes in the front. 3 log base 2 of 2. And we said log base 2 of 2 is just 1. And we're left with 3. That's another way of getting this answer. We could, this is kind of lame, we can change the base. Log base 8. Oh, let's use 2. 2. Oh no, I don't want to do that. Let's go the other way. Oh, let's do both ways. 8 over log base 2 of 2. Like this is the same answer, 1 over 3. Or to go the other way, if I say log base 8 of 8 over log base 8 of 2, this would be 1 over, 8 to what exponent is 2? Turns out if I took the cube root of 8, or you can write this as 8 to the 1/3 power, or 2 cubed to the 1/3 power. That's my exponent. So what exponent gets me from 8 to 2? That exponent is a 1/3. And we don't like dividing fractions, so it's just 3 over 1 times 1, which is 3. So no matter how we cut it, as long as we don't break our rules, we end up with 3, 3, 3, 3. Okay, so the problem that we have on our left-hand side, though, is natural log. And so we said natural log is another way of writing log. Let me rewrite this a little nicer. Ln of A is log base E of A, whatever A could be. So if I write log base, an example is 2 of 2. We did before, didn't we say that cancels out to become 1? So as long as both both the base and the exponent are the same value, well, 2 to the 1 exponent is 2. 2 to the 1 exponent is 2, which makes sense. So if I do this with logs, natural log of e to the 14th power can be rewritten as log base e of e to the 14th. We can do this two ways. We can say that just cancels out to become 1, but more likely is 14 goes in the front, and log base e of e becomes our 1 value. And it's just 14. The problem goes natural log e to the 14 over 2 becomes 14 over 2, which is just 7. Let's go and check that answer. Easy. Okay. This next problem, they're asking us write it in the simplest form. So let's go simplify that. So net log, the base is 1 over 8, 64 is equal to what? So remember, log solve for exponents. If you really want to write this over again, you can write this as 1 over 8 to the blank power is equal to 64. Now this is tough, of course, but I know something. I know that 8 squared is 64, isn't it? 8 squared. So let's rewrite this as an 8 to the negative 1 power of our blank equals to 64. Now, what number do you need this exponent really to be? What number do you need this exponent to be? Negative 1 times what? Well, isn't this 8 squared? So negative 1 equals to 2. Well, 2 has to be negative 2. So it turns out 1 over 8 to the negative 2 power is really 8 to the 2 power, which is the 64 we wanted. That's a win. So what exponent makes 1/8 into 64? Turns out it's a negative 2 power. Negative 2. Let's see how that works. That's great, yeah. So you're going to have to rewrite these problems. Log is 1 over 1,000. It's not 1,000, I'm sorry, 100 is equal to what exponent? Now, what type of log, if I don't write anything? That's what we call a common log. A common log. And common log is always base 10. Log base 10 of 100. Now, what exponent of 10 gives you 1 over 100? Well, first thing, we see that 10 and 100 are related by squared, right? By 2. So I'm going to rewrite this. So 10, so I know it's going to be the question mark is going to be a type of 2. And how do I make something on the denominator? What type of exponent does that have to be? So this has to be a negative exponent. So for 10, negative 2 power is a fraction, and that's 1 over 100. So the exponent I need that solves this, the circle of logs 10 to the negative 2 power, is the 1 over 100 I needed. Answer, negative 2. Okay, let's jump the levels. Let's kick this up. Now, some of these answers here, you can see, you want to really practice your calculator, and there is no way for me to get 5 to 6. And as you can see, they tell us to round to our nearest thousandth. Round to our nearest thousandths here, see? Nearest thousandths. So you're going to be using your calculator here. So we practiced that. We said that this is, if you have a nice calculator with a little button that looks like this, it's like log with a little blank on the bottom and a blank on top. Nice $10 calculator. Instead, if you don't, we said this, we can still do the problem, and you have to know how to do this. We're going to do a change of base. Change of base, log base, common log 6 and a common log 5. And let's just plug it on your calculator. Do I have a calculator on here? I do. So we can say six log divided by 5 log equals 1.11. Okay? 1.11. Oops, in thousandths. 1.113. 1.113. 1.113. And let's see if that makes some sense here. If I write 5 to the 1.113 power, that'll give us a little bit more than 5, and that might take us to 6, right? Okay. So these problems here, you're going to rewrite them using change of base. As a problem progressive is harder. The goal is to not use a calculator when it doesn't ask you for a decimal. Use properties of logs to evaluate the expression. So we're going to rewrite this expression as one log. One big log. So, actually no, I'm sorry. Not in this case. We don't have to do that. This is actually pretty easy. Take that back. Log base 5 of 5 plus log 2 log base 5 of 5. What do we say this becomes? What exponent of 5 gets you back to 5? What exponent of 5 gets you back to 5? Because log solve for exponents. So 1, that's 1. 2 times 1. So 1 plus 2 is 3. Yeah, super. This one doesn't look nice, right? I can't make log base 2 of 3. 2 to what exponent is 3? I don't know, some decimal. So this is going to use our rule. Our rule is that if I'm subtracting logs on the outside, I am back here, right at the top. If I'm subtracting logs, I am dividing. Okay? Yeah, let's go back. If I'm subtracting log, I'm dividing. Let's rewrite this as log base 2 of 3 over 192. Yes, 192 is on the bottom. To rewrite this, I don't know if let's see if can I divide 192 by 3? 1 plus 10 is 10. 1 plus 9 is 10. And then 10 plus 2 is 12. Can I divide 12 by 3? Yes, we can. So this can be divided to become log base 2 of 1 over 3 goes into 19 6 times. 3 goes into 12 4 times. Now, what exponent of 2 gives us 1 over 64? Well, we know that I need to put it as a negative. Let me put a negative here because we need it to go on the denominator. Now, how many 2's does it take us to get to 64? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. Turns out it takes us 1, 2, 3, 4, 5, 6. That's the 6 power. So the goal is to rewrite it first and then we can figure out what the exponent would be. So we're going to say the answer is, what exponent? This answer is -6. Let's cross our fingers. Alright. So you can do the same thing for these other problems. We switch to variables in this version here. But that's fine. Same exact idea. Sorry, let me change back the color. Log y of y is equal to log y, sorry, that's a minus sign, to the 3/5. What happens since they have the same base here? What happens since they have the same base? Sorry, I forgot to write the y here. Let me erase this. Let me do it again. Same base, same base, same base. As the exponent, those go away. Remember, this doesn't become nothing. This doesn't become nothing yet. That doesn't become nothing, right? So so this really is not 0. What exponent of y gets you y? That's going to give us a 1 minus, move that to the front, 3/5. 1 minus 3/5, common denominator 5/5. 5 minus 3/5 is 2/5. Cross your fingers. Alright. Okay. Hopefully that was helpful. We're going to do one more thing real quick. We're going to go ahead and solve these. So we're going to, what is the v value? Log base 4, v is equal to 2. Remember my circle of log song? 4 to the what power is v? So I was covering up the mic for a moment. It's 4 squared is equal to v, and v. 16 is equal to v. That's it. Super fast. Let's jump a couple of these. Get a little harder. Oh, this one was parallel. No. Okay. Solving first. We have to get the ln alone. ln of w plus 5 is equal to 9. Solve for w, minus 5 to both sides. Natural log of w equals to what? 9 minus 5 is 4. Now what did we say was the base for natural log? Or how do we get rid of a natural log? It's we e both sides. E both sides. And that's the inverse operation for logs and natural logs specifically. Okay, so we're left with w is equal to e to the 4th. Now, it's asking us for the calculator to hundreds, so let's go ahead and swap over to our calculator. So 4, shift E, and we're at 54.598, rounding up, 54.60. 54.60. Alright, good work. So my idea here, 12 log of 81, t is equal to 3. We want to get the log alone. So I need to get rid of the 12. Log of 81, t is equal to, divide the 12 to both sides. We can rewrite this, 81t is equal to 1/4. Is that right? Now, we're solving for t. We need to get rid of our base here, my log. So the base is 81 in this case. Do you believe that? 81 is huge, but those are our inverses. So we're going to say it's t is equal to 81 to the 1/4 power. Turns out 1/4 power isn't that bad. 81 divided by 3, 27, 3, 9, 3, 3. We're looking for a set of 4. We do have a set of 4. T is equal to 3. Okay. Thanks, that's great. Okay. And then we're going to do one more. No, we did that one, right? Exponential functions over this one. Okay, so this one we're going to combine values together. Log base 4r plus log base 4 2 is equal to 3. In order to solve it, we need to combine our logs. If we're adding logs, we are multiplying, so we r times 2. And then how do we get rid of this log here, since we're trying to solve for r? To get rid of logs, we use exponents. Exponent of 4, sorry. Our base of 4 to both sides goes away. 2r is equal to 4 times 4 times 4 is 64, which is divided by 2. So the problems are this: just combine them, and then get rid of it. What if I have logs on both sides? Well, that's even easier. 3u equals to log of 2u plus 8. Because since they're the same log, we just have to match what's inside for them to be equal. 3u is equal to 2u plus 8. Now, can we just do that? Well, yeah. But the reason why we can is because if I gave each side the same base, the inverse operation, you still end up with the 3u. Remember that log there is a common log. Now we use our algebra. U is equal to 8. Okay, hopefully you found this helpful. Leave a message if you have any questions, or you can email me.